Hello, welcome back. So the only thing that's changed since the last video is that I got accepted into Georgia Tech, which was my ideal school. So that's why I'm doing a contour integral for this channel, because I was studying recently on it and I'm more comfortable with some of the different contours, like other than just the regular semicircle. And I came up with this one so that it would match one that I recently learned how to do. And yeah, so I've got my classic red rectangle here, which I think, let me verify, yeah, has the light in it so that I know where not to write. Anything else to say? Nope. Let's get into it. So, the first step when we evaluate these kinds of integrals is we have to set up our complex function. So, f of z. F of z is just going to be the integrand, but with x's replaced with z's. So we're going to have root z. And I'm pretty sure for complex arguments, we're supposed to write log z. Correct me if I'm wrong, but I'm pretty sure that's how it's supposed to be. Need an equal sign. Okay, cool. So now the next order of business is to find the poles, which for those of you who don't know, the poles of a complex function are where it blows up to infinity. So let's write poles. So just by inspection, we notice we have a logarithm term, which we all know is discontinuous at 0, because the limit will approach negative infinity. Well, technically the limit doesn't exist, but you get the point. So z equal to 0 is the obvious pole. So now we have to solve for the rest of them, which basically just means setting the denominator equal to 0 here. And then since we have a z to the fourth, we're going to get 4 possible poles, and we're going to have to use all of them. So let's get started with that. And obviously, when this goes to 0, the whole thing goes to infinity. So the way I did it was like this. And then solving individually, we have z squared equals I and negative I. You know where that came from. So then z would be, we have to take the positive and negative roots of these numbers in order to get our full range of possible values. And this makes sense. We've got 4 values, but now we got to turn them into polar form because that would be a lot more helpful. So root I. In the complex plane, I has an argument of pi over 2. And its modulus is 1. So that means we don't have to put any coefficient in front of it. So if I, which means I is going to be e to the I pi over 2. And then when we take the root of that, we're just going to get e to the I pi over 4. Because that's just having the square root just halves the exponent. So we're going to have another pole being equal, well, 2 more poles at plus minus e to the I pi over 4. I'm going to have to keep checking to make sure I'm still recording. Okay. So we have that. And now negative I, we could say is e to the minus, if we, because the angle we're tracing starts at 0 at the positive real axis, you could say that negative I is e to the minus I pi over 2, but I'm going to have a restriction later on which is going to disallow that. So we're going to have to treat, We're going to have to treat negative I as e to the I3 pi over 2, because when you, start at your positive real axis and you turn and you go through 3 pi over 2 radians to get to your minus I, instead of just going negative pi over 2. So yeah. And of course, when we take the square root of that, we're going to get e to the I 3 pi over 4. So our other poles are plus minus e to the I 3 pi over 4. Okay. Yeah. Let's erase this. And the square root isn't going to have any poles anywhere. So let me just draw these out real quick. So e to the I pi over 4 is just a unit vector. Okay, I should make that a vector. Like that. Pi over 4 from the positive real axis, and then its negative is just with a negated radius. And then for e to the I 3 pi over 4, it's similar, but we just go here, and its negative is here. So these are our locations of the poles. Okay, cool. So now our next step is to define the contour, which there's a few that I've been like toying with, but this one's cool, so I'm going to use this one. You'll see what it is. So we're going to have this. This looks a little long. Okay. So let's first immediately notice, like we said earlier, we have a pole at 0. But the thing is, we're not going to be able to work with that pole. We can work with these poles, which we're going to find the residues. Most of you already know that, but for those of you who don't, that's what is going to happen. We can't find the residue at 0. At least I don't think. I'm not good enough to know. But as far as I know, we always just avoid 0, so that's what we're going to do. We're going to avoid 0 on our contour, which, by the way, I need to label as the real part and imaginary part. Okay, so this is what we're going to do. I can use black. So, if we want to dodge 0, that means we cannot hit it. We cannot enclose it either inside of our contour. So, what we're going to do is we're going to have a little circle. We're going to have a little circle that has a radius epsilon. But since I wrote it to the left, we're going to have to call it negative. I have to write this is negative epsilon. So yeah, this is a poorly drawn circle, but it has a radius epsilon. And what we're trying to do is see what happens when that radius just shrinks to 0, aka so that it will converge, like this circle will converge to the origin, and we'll be able to have, we'll be able to integrate at 0. Okay, now, another thing we have to do, I'll briefly demonstrate why. We're going to need a branch cut along the positive real axis because root z, so also, let me write this because I'm going to forget this. We need to define the limits for our argument over a complex number. So, I'm not entirely sure if this is correct. I mean, I know it has to be 0 and 2 pi. I'm pretty sure this is less than or equal to. I don't know if this is going to be less than or equal to because we're trying not to have it hit 2 pi, but you can correct me in the comments if that's wrong. But anyway, so now, square root of z. This is a problem because any complex number, z, can be written as its modulus, which, yeah, it can be written as its modulus, so let's say a length r, times e to the I phi, yeah? Okay, so phi is just the angle from the positive real axis that your complex number makes. So that means that root z is equal to root r, and then when we take, so we're taking the root of both sides, which means we're going to get I phi by 2. So what's the problem here? When we start at 0, when we start at phi equal to 0, this exponent goes to 0, which means this exponential turns into 1. So, okay, but if we take a full loop and we come back to the exact same place, we're in the same place as we started, but we've done a 2 pi rotation. If you plug in 2 pi into here, you'll get e to the I pi, which is negative 1. So at 0, root z would be just square root r, but after a full rotation back in the same place, it's actually negative root r, which means it's multi-valued. So with this in mind, we have to take a branch cut, which is basically like excluding the positive real axis. And again, I may not be explaining this right, because I'm no expert, so please correct me if I said anything inaccurate there. Anything else? Nope? Okay. So we're going to have these lines. Hold up. That's too wavy. I'm going to have lines going parallel to the real axis, but not on it. trying to be very careful so I can draw these straight. Probably should have given myself more room to write, but it's fine. So we're going to have these lines that are, let me make little arrows here and to here, indicating these are each a distance d away from our positive real axis. So one of them is a distance d above, one of them is a distance d below. So what we're trying to do with d, which maybe I can write that in black, we want d to go to 0. Similar to this little circle, we want the distance between these lines and our positive real axis to just go to 0 so that we can properly evaluate our integral. So we'll cover that later. And then the rest of this, we're just going to make a very large circle. Okay, that could be a worse drawing. Okay. And we always, let me establish. Our radius of this circle is going to be r, which means we have negative r over here. We want r to tend to infinity, because if you know our target integral is from 0 to infinity, we want this as epsilon goes to 0, and as r goes to infinity, we'll have just this integral along the real axis, because keep in mind the distance is going to 0, so this is effectively going to be on the real axis, so there's no more dz. It's not an f of z function anymore, it's just a real function. And if we integrate from 0 to infinity, we get our target integral I. So as we start naming these contours, I can immediately start off by calling this one I, because we know that as epsilon goes to 0 and r goes to infinity, we're integrating our f of z, which is technically f of x if we're on the real axis, because there's no imaginary part. That'll give us our target integral I. And I know that a lot of people use big gamma for the big circle, so that's what I'm going to do, and little gamma for the little circle. Okay, I don't really know why, but I just see that's what everyone uses, so I'm going to fall in line. And now we've got this one, which another Greek letter I see people use for contours, we're just going to call psi, if it is visible. Bear with me. No. Apologies. Sorry. All my markers are fading. I don't overuse them, I just use them a lot. Okay. So, let me make sure. I have to make sure I get all the details here, because there's like a lot of things I have to write about this integral. Okay, and we always evaluate in the counterclockwise sense. So we're going to go like this, like this, like this, just following the arrows. That's the direction we're integrating in. And now I think we can set up our equations. Oh, no, haha. Okay, we have to put our poles. So I almost forgot that. So our poles are located like here, if those are our complex planes. So I'm just going to put x's to denote where the poles are. Roughly, it doesn't really matter. All we need to know is that they're inside of this contour. So now we can eliminate all this. These are still important. But anyway, so we have the integral over the closed contour C, which I did not name. The whole thing's going to be named C. Should have wrote it in blue, but whatever. So the whole integral over the contour C is going to be equal to, we have to sum up all the little integrals, basically. Not necessarily little, but all the smaller parts. So we have the integral over big gamma, because that's our large circle, and then plus the integral over psi, plus the integral over little gamma, and then plus our target integral I, which basically would be the integral from 0 to infinity of our function, which again is just I. Now, this is also equal to, using the residue theorem, 2 pi I times the sum of the residues of our complex function. So, yeah, I'm sure some of you are already seeing that we're going to have to do 4 residues, which we are, but it's fine. We'll deal with it. Yeah. So, is there anything else I need to say or that I forgot? Nope. Okay. So, I'm just going to write residues. We need to find the residues at each of these poles. We don't care about this one, because that one's just excluded from our graph. So we'll start with z being equal to e to the I pi over 4, the positive version. So, and this is a simple pole, by the way, because it, like, the factor of z minus e to the I pi over 4 doesn't occur more than once. So it is a simple pole. There's no differentiating. We're fine. Okay, so, and that's defined as, the residue of this, of a simple pole, is defined as a limit as z approaches your pole of z minus your pole times your function f of z, which is root z log z over z to the 4th plus 1. So, now, let's just establish something. When we plug in z equals e to the I pi over 4, this term goes to 0, which sends the numerator to 0, and we already know this is a 0 of the denominator, so we're going to get an indeterminate form, which means we need to use L'Hopital's rule. And when I was practicing these similar integrals on my own, I noticed we saw there's like this cancellation that happened every single time. And then I remembered, like, when I first got into integrals, I saw a Maths 505 video, and I remember he said something about simple poles that, like, you can keep the top, differentiate the bottom. I didn't know what that meant until yesterday when I tried to, like, I don't know, generalize what was happening with this little thing. So I'm going to generalize it now so that we can save time in the future. You'll know what I mean. So let's generalize this case as the limit as z approaches some other complex number w, which is your pole of the function, z minus w times a function of z you have on top over a function of z you have on the bottom. So this is like a different f of z. This is just an example. Okay, so now if we know, we would only be doing this if w was a pole of the function, so it's a factor of the denominator, which would send it to 0. So this is indeterminate, which means we can use L'Hopital's rule, so let's do that. So when we combine these terms, z f of z, and we differentiate that, we're just going to get f of z plus z f prime of z. And then this w is just a constant, no matter what it is. So it's just going to be minus w f prime of z upon differentiation. And then we have g prime of z. Now, I should make this an arrow. Now, as we plug in w for z, this will turn to a w, this will turn to that'll turn to a w, this will turn to a w, this will turn to a w, and as will this. But now notice, we have f of w plus wf prime of w minus wf prime of w, which these two conveniently cancel out. So that means, when all is said and done, this limit is equal to f of w over g prime of w, which tracks with what I heard Kamal say in that video a long time ago. Keep the top, differentiate the bottom. Great. So now, whenever we have this sort of setup, we don't have to differentiate and use product rule for this. We could just plug our pole into this little mini expression. Okay, so using that, we're going to have the square root of e to the I pi over 4 is e to the I pi over 8. And the log and the e would cancel, which will give us times I pi. I'll bring the 4 to the bottom because we're differentiating. So we're going to have 16. Remember, it's going to be 4z cubed here. And then when we plug in this for z, we're going to get e to the I 3 pi over 4. And now e to the I 3 pi over 4 is, 3 pi over 4 is 6 pi over 8, which can help us cancel the stuff on the top. So we'll just get, at the end, I pi over 16 e to the I 5 pi over 8. Okay, that's one residue. Now, for z equals negative e to the I pi over 4. We know we're going to have the same setup, but with a negative e to the I pi over 4, but we're just going to skip it and use that. So we're going to have the square root of negative e to the I pi over 4, which I will get to, as well as the logarithm of negative e to the I pi over 4. And then we're going to have a negative because when we have 4z cubed and we plug in a negative for the z cubed, the negative is going to stay. So we'll have e to the I 3 pi over 4. Let's make sure we're still recording. Great. Okay. So now, this square root, we can split it as the square root of negative 1 times the square root of e to the I pi over 4. Square root of negative 1 is I, and the square root of this is e to the I pi over 8. So this is going to be I times e to the I pi over 8. And then this logarithm we can split into logarithm of negative 1 plus the logarithm of e to the I pi over 4. So log of negative 1 is just I pi because e to the I pi gives us negative 1. So we're going to have I pi. And then we have a plus. The e and the log are going to cancel out, so we're going to get I pi over 4, which we can, of course, combine into 5 pi I over 4. But I'll carry the 4 to the bottom, so we'll have minus 16 e to the I 3 pi over 4. Yes? Okay. Now I want to notice something. This I and this I are going to multiply each other and negate the whole expression. But we already have a negative, so we can, in fact, just disappear all the i's and the negatives. Well, except the ones in the exponential. Now, using the same simplification we did last time, we know we're going to get 5 pi over 16 e to the I 5 pi over 8. That's our second residue. Here I just, again, canceled out the e on the top. So that's another residue we have. Now for the next one, z being e to the I 3 pi over 4. Let's just plug it into our handy dandy little thing here. We're going to have, so the root, okay, e to the I 3 pi over 8, right? Let's just verify. Yep, okay. E to the I 3 pi over 8, and then the logarithm, which will be 3 pi over 4. No, 3 pi I over 4, and the 4 will come down here. So, when we have the 4z cubed, which we already took care of before, when we cube this, we're going to get e to the I 9 pi over 4. But that would violate our restriction of the angle, because our angle is greater than 2 pi. So we have to sort of, I don't know if normalize is the right word, but just set it back to, you have to subtract 2 pi until we get it within our range, which we only have to do once. So e to the I 9 pi over 4 is the same thing as e to the I pi over 4. Like that. Which we can now simplify, because this is e to the I 2 pi over 8. We'll have we'll have 3 pi I e to the I pi over 8 over 16. That's another residue. Now for z equal to negative e to the I 3 pi over 4. So when we do the square root again, we're just going to get I e to the I 3 pi over 8. And then the logarithm, similar to before, will just be I pi plus 3 pi I over 4. This is going to be minus 4, and then we still have to do the same, subtract 2 pi thing from the angle, I'm going to have e to the I pi over 4, I believe. Yeah, okay. So this is, I can do this more efficiently. Combining these two is just going to give us 7 pi I over 4. So times 7 pi I. 4 will come down, turn this to a 16. And then, similar to before, we notice that the I will make this I a negative 1, which will cancel out the negative here. So those can just vanish. And then we factor out again. This will give us 7 pi e to the I pi over 8 over 16. Okay, that's another, well, actually, that's our final pole. Great. So, now keep in mind, we have to sum the residues of f of z. So yeah, I'm going to use an arrow to point to this, which will indicate we're summing them. So now we just have to add these together, multiply 2 by I, and we'll have what this entire contour is equal to. It's not going to be the value of our target integral yet, but we're going to have to play with these before we get our final answer. Anyway, so let's quickly factor out a pi over 16, because each of these terms has a pi over 16 in common. So that's valid. Now, for the first one, we're just going to have, we're just going to have I, and then I'm going to rewrite this 1 over e to the I 5 pi over 8 as just e to the minus 5 pi over 8. Excuse me, it's a lot of talking. Okay, so then next one, we're just going to have plus 5 e to the minus I 5 pi over 8, right? Yep, because the pi and 16 are gone. Then this one, we're just going to have plus 3i e to the I pi over 8. And then this one, we're just going to have plus 7 e to the I pi over 8. Okay, so that's the sum of our residues. Now, I'm just going to quickly multiply 2 pi I. So, the 2 will turn this denominator to an 8. The pi will make this squared. And now let's just multiply I into each of these terms. Okay, we're still going. So, the I will make this negative. I here. This will become a minus 3. Then we stick an I there. Okay. But now I want to separate this into real and imaginary parts, which means I'm going to have to expand all these using Euler's formula. Fun. So that means we're going to have pi squared over 8. Now, e to the, there. So we just know that e to the I theta is cosine theta plus I sine theta. So we have e to the minus I 5 pi over 8. So cosine's an even function, so cosine of negative 5 pi over 8 is just cosine 5 pi over 8. But since we're negating it with this outside negative, we're going to get minus cosine 5 pi over 8. Sine is odd, so we're going to get minus I sine 5 pi over 8, but the negative will fix that. And this one will give us 5i cosine 5 pi over 8. Because again, cosine's even, and then we just multiply it by 5i. And then sine's odd, so we're going to get minus I sine 5 pi over 8, but the 5i will fix that to a 5 sine 5 pi over 8. Right? Yeah. Okay. Then next, we're going to have minus 3 cosine pi over 8 minus 3i sine pi over 8. And then finally, we're going to have 7i cosine pi over 8. Right? Yeah. And then minus 7 sine pi over 8. think that's it. Should have 8 terms, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now, I want to do some trigonometry here. I want to get rid of the 5 pi by 8 things so that we can combine some like terms. So, let's just draw a quick graph. It's a bad graph. Straight lines, please. Better. Okay, so let's say we have this. Okay, it's fine. So theta equals pi by 8. And now let's draw this, where we have that. This is supposed to be at the origin, so I'll just put a dot to cover up my error. Okay, so when we take the cosine of 5 pi over 8, as we have here, that means this, we're looking for this horizontal distance, which, not drawn to scale, so let me write, just for some of you, this x value is going to be the same as the y value when theta is just pi over 8. But we have to keep in mind we're in quadrant 2, so cosine is negative. So that means cosine of 5 pi over 8 is actually negative sine pi over 8. But we have a negative here, which will get rid of the other negative from the transformation. Okay, so now we have sine 5 pi over 8. So now we'd be looking for like the y value here, which is the same as the x value when theta is pi over 8. And since it's in quadrant 2, it's also positive. Sine is positive, so that means sine of 5 pi by 8 is just cosine pi by 8. My voice is getting hoarse. Okay, this we already established can be changed to negative sine pi over 8. Okay, this can be changed to cosine pi over 8. Again, just same process. Yeah, okay, we've got everything in terms of pi over 8. So now, let's combine some terms. Okay. So, geez, there's some wind. I want to separate this into real and imaginary parts also, because that's kind of important. So, let's check how many real sine pi over 8s we have. We got 1, and then a minus 7. So that's going to be minus 6 sine pi over 8. Then how many real cosine pi over 8s do we have? We have 5, and then minus 3. So that's going to be plus 2 cosine pi over 8. Now, I'm going to add and factor out an I, because again, real and imaginary parts. Okay, so cosine came first. So how many imaginary cosines? We've got 1 and 7. So that's going to be 8 cosine pi over 8. And then how many imaginary sines? Minus 5, minus 3, minus 8 sine pi over 8. And nice. Now, I will say we can factor out a 2 here. So I can change this to a 3. Get rid of this 2. Change these both to 4. And turn this 8 to a 4 as well. Okay, cool. So, yeah, that's what our entire contour is equal to, but obviously this isn't our final answer because we have imaginary parts. Our integral is entirely real. But I can replace this with our expression. I'm going to have to write vertically. So we're going to have pi squared over 4, big parentheses here. I'll just flip the order of this. We're going to have cosine pi over 8 minus 3 sine pi over 8 plus I times 4 cosine pi over 8 minus 4 sine pi over 8. Yeah? Cool. So that's what this entire contour integral will evaluate to. Now I can erase a lot. That was the sort of like boring part. I mean, to be honest, I didn't find that very boring, but I'm sure from a viewing perspective, it wasn't very engaging. But at least the next stuff is kind of more fun, where we play with the integrals that are here, the ones in our contour. So let's start with big gamma. So we have the integral over big gamma. So this is a large circle, which means any complex number can be parameterized as re to the I phi. So the reason we have r is because this is a circle of radius r. So just using polar coordinates, that's what you get. And then we differentiate dz equals ir to the e I phi d phi. And now let's do our integral. So as d goes to 0 and our epsilon goes to 0, we're basically integrating from 0 to 2 pi. Our phi is going from 0 to 2 pi along this circle, because it's a full circle. Now, from a differential element, I'm just going to pull out an I out front. Now, we basically have to take our function f of z and substitute this into z. So, the square root of z will be first the square root of r, which we get another from the differential element. So, root r times r will be r to the 3 halves. And then we'll have e to the I phi by 2, because that also came from the square root, times, and now the logarithm can be split as just ln of r. We can do ln this time because r is just a real number, it's just the radius of the circle. And then plus the log of this, which is just going to be I phi. This is all going to be over... Oh, and from the differential element, we also get another e to the I phi. So when we combine these, we can just make that a 3 phi over 2, which I will rewrite so you can see. Okay, then we have just z to the 4th, which will be r to the 4th e to the I 4 phi plus 1 d phi. Okay, now, remember what we said at the beginning, which I guess I may have forgotten it then, but I'm not going to forget it now. We want epsilon and d to go to 0, and we want big R to go to infinity. I should have defined that earlier, but it's fine, I explained it. So that means we want the limit as r goes to infinity here. So let's first notice that when we FOIL these terms out, the one that has this I phi in it, that doesn't have the ln r, when we take the limit as r goes to infinity, we have basically r to the 3 halves over r to the 4th. And the r to the 4th will just outrun that one every time. So this term we can forget about. So now, these two are really just constants right now, or we don't really care about them. So what we're really looking for is a limit as r goes to infinity of r to the 3 halves times ln r over r to the 4th e to the, let's say, 4 I phi plus 1. Okay. Now let's verify I'm not going to do anything wrong. Okay, so let's divide the numerator and the denominator by r to the 3 halves. So we're going to get ln r over, okay, so r to the 4th over 3 halves, so that's basically 8 halves minus 3 halves, which is going to be r to the 5 halves e to the 4 I phi, then plus 1 over r to the 3 halves, right? Yeah. Okay, so now this is going to be obviously indeterminate because as r goes to infinity, we have infinity over infinity. So you know what that means. We're going to differentiate. We got 1 by r, and then this is just a constant, so we're just going to get 5 halves r to the 3 halves e to the 4i phi, which is annoying to write even though we don't need it. Then minus 3 halves times 1 over r to the 5 halves, right? Let's just make sure. Okay. And now, when this r comes down, so it's just going to basically multiply, we're going to add 1 to each of the exponents. So that's going to be 1 over 5 halves r to the 5 halves, which is what we had before, e to the 4i phi, and then minus 3 halves. This will go in the numerator of the denominator, so that's just going to be times 1 over r to the 3 halves. Now, we take the limit as r goes to infinity. This term goes to 0. This term goes to infinity. This entire limit equals 0. So, we've established that the integrand will turn to 0 as r goes to infinity. Let's make sure we're still recording. So that means integral over big gamma will go to 0 as r goes to infinity. Okay, good. That's 1. Now, I want to adopt a similar process for the integral over little gamma. So we can do the same thing, except we can parameterize z as epsilon e to the I phi, because our circle has a radius epsilon. And then that means dz is equal to I epsilon e to the I epsilon, no, e to the I phi d phi. So then we still have an integral from 0 to 2 pi, because remember we're trying to converge, we're trying to make d 0. So that means we're going to have 0 and 2 pi. And then same as before, we have an I. We're going to have an epsilon to the 3 halves after everything is said and done. We're going to have an e to the 3i phi over 2. And then we're going to have ln of epsilon plus I phi. All over epsilon to the 4th, e to the 4i phi plus 1 d phi. Great. Okay, so now, this time instead of taking the limit as r goes to infinity, we're taking the limit as epsilon goes to 0. So, okay, using properties of limits, the denominator does not go to 0. The denominator just goes to 1. So the product of a limit is, the limit of the product is the product of the limit. So we can essentially ignore this because this just goes to 1 as epsilon goes to 0. So we just have to multiply that times the limit of this, which, you know, this is just a 1, so we can effectively remove this from consideration, from the limit, that is. So then that leaves us with, oh, and also when this term gets distributed to the I phi, obviously as epsilon goes to 0, this will go to 0. So now the only limit we're looking for is the limit as epsilon goes to 0 of, again, these are just constants, we don't care, of epsilon to the 3 halves times, not r, ln of epsilon. This is a very famous kind of limit, but whatever. So this is just the same thing as ln epsilon over epsilon to the minus 3 halves. So then, obviously we have, so it's an indeterminate form anyway, because we have 0 times minus infinity. So in essence, this is also minus infinity over infinity. So we can differentiate 1 by epsilon over minus 3 halves epsilon to the minus 5 halves, which is equal to minus 2 thirds times 1 over epsilon to the minus 3 halves, because this fixes that. And since epsilon has a negative exponent, we can just negate it and put it to the top. And as epsilon goes to 0, this goes to 0. So this entire thing goes to 0 as well. Okay, we're getting somewhere. Now, we're almost done. We just have to focus on the integral over psi. So the integral over psi, we can do another similar thing. Any complex number can be written as the modulus, because this time our angle is set, but the length, because remember here, we have a set angle, but our the modulus of the complex number isn't the same everywhere. So that means we can still write it as the modulus of z times e to the I, and keep in mind, as this distance goes to 0, we're closing into an argument of 2 pi. So we're going to have e to the I 2 pi. And now this modulus, as we make this distance 0, is just going to be, this line is going to be basically on top of the real axis, which means the modulus of a complex number there would just, it's a real number on the positive real axis. So its modulus will just be itself. So that means when we differentiate, our old dz will be equal to just e to the I 2 pi with our new dz, because that's basically the only variable we care about. So if we can parameterize it this way, this will give us the integral, hold up. So since we start here, we're going from r, which is, as we said, infinity. Well, we said it's tending towards infinity, to epsilon, which we said was going to be 0. And then, hold up. Yeah, okay, we're good. So I just want to mention, e to the I 2 pi is just 1. So I remember this didn't come up when I solved the integral to begin with, but yeah, this is 1, so we don't actually have to worry about this. So, anywho, when we take our square root, so the square root of this, we're still going to have root z times e to the I, now pi, because we have to have this as it's part of the square root. And now, the logarithm of this can be split into ln of z, and I'm using ln z here just because it's going to be effectively on the positive real axis, so it's a real number, so I'm going to use ln. And then plus the logarithm of this, which is just going to be 2 pi I. And z to the 4th, so keep in mind, this is just a 1, essentially. Well, when we plug this into z to the 4th, we're going to get z to the 4th. And then when we raise this to the power of 4, we'll get e to the I 8 pi, which is still just 1, because it's just 4 rotations back to the original starting point of 0, so that's just 1. So we just get a plus 1 here, and then this is our new dz. So now what I want to notice is we have an e to the I pi here, which we all know to be -1, so we can put a negative here, and then immediately use that to switch the bounds of integration. And now we can split this, so we'll have the integral from 0 to infinity of root z, well, no, since we're on the positive real axis, we have ln x, right? Ln x, I should write root x first. Root x, ln x over x to the 4th plus 1, plus the integral from 0 to infinity. But we have this 2 pi I next to it from this coefficient. So I'm really just foiling. I'm just multiplying this times this, and this times that, times root z over z to the 4th plus 1 dz. And this is exactly our original integral I. So, and this is an imaginary, well, this integral is also real, so I should have put x's here, but it's connected to an I, which you'll see why that is cute soon. So this goes to I plus 2 pi I times the integral from 0 to infinity of root x over x squared, no, not x squared, it's to the fourth plus 1 dx. So now we can actually, we're pretty much almost done. You can use the trick where we compare real and imaginary parts on both sides because they must be equal, assuming we did everything right, which I did. So we have a 2i on this side, so that means 2i must be equal to pi squared over 4 times cosine pi over 8 minus 3 sine pi over 8, and also we have that 2 pi I times the integral from 0 to infinity root x over x to the fourth plus 1 dx must be equal to, these 4's are all going to cancel out, so we're just going to get pi squared times cosine pi over 8 minus sine pi over 8. This will cancel this. And then if we divide this, we get that. So what's nice is, you know, I'm gonna solve this, don't worry. But it's just that throughout this entire process, we just get this bonus integral right here, which is also not easy to evaluate. You have to use the same method, I think. But like just by comparing the real and imaginary parts, we get the answer. The answer to this integral is pi by 2 times cosine pi by 8 minus sine pi by 8. So we didn't even solve this integral, and we just got the answer. So I just thought that was cool. But anyway, here, our target integral I is equal to pi squared over 8 times cosine pi over 8 minus 3 sine pi over 8. Now, I do want to say something. I don't like leaving my answers in trigonometric form, so I'm going to do the extra step and reduce it. But first, the trick I'm going to use requires that I acknowledge this is a negative number. So I'm going to pull out a negative here, turn this to a plus, and make this a minus. So then I can figure out what this is actually equal to. So I'll just say x equal to 3 sine pi over 8 minus, and I know this is extra, so you might have clicked off already, but whatever. Let's make sure we're still recording. Okay, so this is, I'm just going to set this equal to x. And then I'm going to square it, because now it's positive. Because basically what I was going to do is square it and then take the square root. But if I did that, I'd get a positive number back. So I have to make sure I've accounted for this negative. So, anywho, this is equal to, if you know the values of these, that's going to be 3 root 2 minus root 2 over 2 minus root 2 plus root 2 over 2. That's the values for these trig functions. But obviously, I don't want to leave them like that. So then when we square it, we're going to get this term squared, which is going to be 9 over 4 times 2 minus root 2. And then we're going to get plus this, which is just going to be 2 plus root 2 over 4. And then minus double the cross product, which is going to be minus 3 over 2 root. And then these two terms are just going to multiply together and get a difference of squares, which will be 4 minus 2, which will just be root 2. So I'll shorten that square root. And I can actually change this to a 4 and make this a 6 just so we can combine. So that is going to be equal to 18 minus 9 root 2 plus 2 plus root 2 minus 6 root 2. Right? Let me just verify. Okay. This is going to be all over 4, yes? Okay. So this is going to be equal to, so we're going to have a 5 because this 18 plus 2 divided by 4 is going to give us a 5. And then our root 2's, we have minus 15 and then a positive 1, which will give us minus 14 over 4. So minus 7 root 2 over 2, which is in fact 5 minus 7 by root 2. And then we can just take the square root of that to retrieve our x back. So we're going to get root 5 minus 7 over root 2. So then, after all that, so you see, we actually managed to condense the term into something nicer. Finally, okay. So, I wrote this in an inopportune place. So, our target integral I is equal to negative pi squared over 8 times, I don't need that, times the square root of 5 minus 7 over root 2. And just a little bonus, we get that the integral from 0 to infinity of root x over x to the 4th plus 1 dx equals pi by 2 times cosine pi over 8 minus sine pi over 8. I'm not going to reduce that because there's not much I can do. So, oh my goodness. That took a while, but I like doing this kind of stuff. Is very long, but I'm happy. Plus we get this little bonus result, which I thought was neat. Yeah, okay, that's it. Like and subscribe.